Good morning. In 2003, NASA sent up the last mission of the Space Shuttle Columbia, which contained one of the most perplexing and extraordinary and probably little-known experiments that has been sent up on space shuttles to date. This carried an experiment that was initially developed by my research partner at Johnson Space Center, Dr. Tom Goodwin. It was essentially set up here to take a model of bone stromal cells and prostate cancer cells and study the relationship and the metastatic potential with prostate cells and bone in a microgravity environment. And so Tom's laboratory, in collaboration with ours, works on three-dimensional tissue biology models as disease analogs for human diseases. And so the goal was to send up this model into space and look at how this would behave in the space environment. So this is a rotating bioreactor containing this cell type. And it was sent into space for 16 days on the Columbia mission. So these are real-time synced images of the Earth-based prostate cancer cell bone stromal cell model. And this is a time-synced image with what was happening on the Columbia mission during flight. After only 5 days in space, tumor aggregates began to form that were about golf ball sized. And if we took this all the way out to its conclusion of the 16-day mission, we found that after 16 days, it aggregated into a single fist-sized tumor. This was extraordinary. What were the implications of this? And what triggered the formation of this tumor in space? And what can that tell us about personalized medicine as we try to translate these findings from extreme environments and space conditions into Earth-based medicine? So the question is, was that radiation? Because we had no similar cellular changes in the Earth-based environment. Was it related to microgravity? Was it related to an absence of a geomagnetic field that we would typically find in the Earth-based environment? The thing is, we don't know. Because as you know, the Columbia mission burned up on re-entry. So all of this specimen that would have been analyzed back in the laboratory at Johnson Space Center never returned. So we don't know, but we're left with an enigma that says massive tumors may form in space, and we really don't understand much about that. Obviously, this did not have a suppressive immune system and a range of things that would have helped contain tumor development in space. But it presents us with a serious enigma. But it opens a door for discovery. And so that's the question, how do we find out? When we're presented in a clinical environment with an enigma like this, how do we proceed? One of the areas we want to focus on, and some of that was just discussed, is we look at SNP profiling, we look at genomic profiling. Secondarily, we would look at transcriptomics. So with this enigmatic sample, what we would have done is looked at genome, SNP profiling, transcriptome, and of course proteome, and then metabolome. And this really starts to form the foundation of how we would answer any very difficult question from a research standpoint, but it also opens the door to asking some of these similar questions, embracing this complexity in a clinical setting. So the basis of this going forward then is our first tenet, and that is that we can use systems biology to help us describe variant outcomes between diseases and conditions. And I want to highlight one converging element that we're seeing increasingly in research and in medicine, and that is of hypothesis versus non-hypothesis driven discovery. Much of medicine, and perhaps most, is hypothesis-driven, as it is within research. What we're getting now with the omics disciplines is the ability to measure thousands of genes, thousands of proteins, thousands of small molecules, where the data begins to generate it. So increasingly, we'll see the convergence of hypothesis and non-hypothesis-driven discovery in the clinical setting. So then this moves to another phenomenon, and gradually what I want to get here is a concept and a core thread that's going to reside in this entire discussion of where personalized medicine may go. And this is an enigma that we face now in human spaceflight, which has tremendous elements germane to medical practice on Earth, and that is ocular disorders in space. This is an urgent problem. Right now, outside of radiation, ocular problems in spaceflight is one of the most pressing problems at NASA and in the commercial spaceflight sector as well. Why do humans develop these ocular problems in space? More than 20% of the astronauts on the International Space Station who have been there for more than 4 months develop a range of ocular problems, increased intraocular pressure, intracranial pressure.